Okay, so we are going to talk about data structures for computer graphics. But before we start this, I just want to summarize everything we have learned up to now, so that if you have any questions, any parts that you don't understand, please let me know. Okay, so we have seen our first algorithm for computer graphics to be able to generate a photograph of a virtual scene. And the way we do that is in the ray tracing algorithm. We have an algorithm for each pixel. Each pixel is like a pinhole camera into the world, and we find the color, we find some detailed color for each pixel, and the other pixels are independently computed their colors from the other pixels. So we have a main for loop which goes through all the pixels in our image, and we find their colors, and then we construct our image. This image, we can write it to a file, like a PPM file or some image file. But in computer graphics application, interactive applications, our goal usually is to write this image on the screen and dynamically update the image as things in the scene change dynamically. For example, as the camera moves, for example, the camera may indicate the view of some avatar, that if you're in a, for example, first-person shooter game, the camera may be the eyes of a player that you're playing, and as you move around in the scene, you may want to update the scene very fast to get an interactive, real-time feeling. And ray tracing, therefore, I mean, if it should take at least 1/25 seconds to render a single frame, so that we have a smooth feeling of smoothness, as if it's a movie. So we haven't done that with ray tracing yet. We are doing what is called off-screen rendering. We are rendering our photograph to an image file, and then we see how those images look like. If interactivity is not a problem, for example, if you're generating these images for a movie, for a CGI animation, what you can do is actually, it's okay that these frames take long time to render. Even if it takes 1 minute for each frame to render, you can actually render them in a long period of time. You don't need to, the total rendering time does not need to be equal to the duration of the movie. You can spend 1 year to render the entire thing, but it may just be a 5-minute animation. Okay, so but at the end, after you have those images, you just stitch them together into a movie file, and this is how you get your CGI animation. So that's why, for example, in the beginning of 2000, at the end of 1990s, the first long version CGI animations, they actually took a long time to render. They had rendering farms to do these things. But these days, we have some interactive, very high quality rendering with the help of GPUs on our desktops. So, okay, so this was a side note, but let me just go over the ray tracing algorithm, in which we have a ray that is going through the center of a pixel. So I'm not going to draw the entire image plane, but what we have is we have a viewpoint here, the focal point of our rays originating, and the rays that are the reason that the rays are originating from here and going in kind of like a pyramid kind of shape actually is the reason for perspective view. We could have generated rays with parallel to each other, not have a point E like this. In other words, E could be at infinity. In that case, I mean, imagine, I'm going to erase this image plane, but imagine we have an image window like this, and all rays are parallel to each other, and whereas they are passing through the center of these pixels. Okay, so we don't see it like this in our real life naturally, but what may be the benefits of such visualization? Why do we want to have rays parallel to each other? First of all, we will be losing perspective, but can someone benefit from losing perspective? For example, objects appearing exactly the same sizes. Exactly, that's a very good point. For technical drawings, for example, if you're an architect or some mechanical designer, the perspective visualization actually does not help you in understanding the dimension of things. So as things, for example, get distorted, as they get smaller, as they get far away from you, you may not understand their relative sizes. So this is what it's called. This is called an orthographic projection. So you may have, if you see this term, we are going to talk about these in detail when we start talking about OpenGL, and actually when we talk about projection transformations, we will see how orthographic projection can be done. But we will see this in the forward rendering pipeline. We'll see an alternative algorithm to ray tracing to generate the photo of the same scene. But yeah, this is also lots of different things are possible in ray tracing. I mean, the basic version that we have shown is just the most basic standard version of ray tracing. For example, we may have the entire image plane not as a rectangle like this, but it may be, for example, spherical. Part of it, for example, instead of this image plane, could imagine this image plane was inside some sphere. It may be the surface, inside surface area. Imagine we have a sphere like this, and our image plane could be part of the sphere that is inside, so we can have actually a curved kind of screen that we are rendering on. So it may have an interesting effect. I mean, if you write it to a flat image file, which is rectangle, our image files are rectangles, that's why they're matching. But if you have something like this and render it to a, maybe you're rendering it a spherical screen, you will see it with no distortion, and your screen will be spherical. Okay, so there are different alternatives. I just wanted to show you it's possible to have different ways to get ray tracing running. Okay, now let's get back to our summary of what we do in ray tracing. So I'm going to actually have this E here, our pixel here, to show that how we have a sphere like this, for example, the interaction, to show the interaction with the surface, I'm going to have this ray like this. This is our center of a pixel. Okay, so what do we have? So we have this object, we have its color, the reflectance coefficients given to us as, for example, let's call it K, as RGB values, KR, KG, KB, which may be the color of this object, saying that how much of the radiance, which components of the radiance are reflected at this point of intersection with our ray with the surface of this object. So we have material properties. In addition to just these reflectance coefficients, we may, for example, have the Phong exponent, the specular exponent we have, which may be given to us as another variable named S. How shiny is the surface? Also, the reflectivity, how mirror-like, mirror reflection. What is the amount of mirror reflection we have from this? Let's call this M, for example. These are given like scalars, but the mirror reflection could also be given as the reflectance coefficient, where it has different mirror reflection, may have different levels at different color channels, RGB, or it may just be given as a scalar, meaning that it's the same for all red, green, blue channels. Am I missing anything about material properties? So I know that another material property is whether the surface is sphere or triangle. That's what you have implicit with this surface object. But I guess that's it for this surface object. Mirror reflectivity coefficient, its specular exponent, its color. In some systems, this color, the reflectivity coefficient, this reflectance coefficients, Kr, Kg, and Kb, may be given separately for each of those ambient, diffuse, and specular components. So it's something really unnatural. It's like, in terms of the ambient light, this is like a red sphere. You can specify it as a red sphere, but in terms of a diffuse color, it's like a blue sphere. Some systems, OpenGL, for example, allows you to do this. It allows you to provide 3 separate colors. For example, for specular, it just the specular spot, you just may want to appear it as a white specular spot. So you may say that the specular light is reflected as a white surface, but this diffuse and ambient may be of different colors. So this reflectance coefficient may be given separately for different components, but it's real. I mean, physically, this doesn't make sense, right? I mean, physically, if the material reflectance coefficient is a property of its material, so it shouldn't change from basic elimination model component to component. So just a side note, just know that if when you face something like that later, don't get surprised. Okay, we are free to play with some unnatural physics. We can propose some unnatural physics because this is our. I mean, we are limited by our imagination. We can have materials that with interesting properties. Another thing about the surface is at this intersection point. Now let's go to the vectors we have. We have the normal vector. Okay, and all these vectors are actually, this is our ray, and this is our ray's direction. But at this surface point, when we are doing our computation, we treat all the vectors as if they are coming out of this point P. So this is the intersection point P. All the vectors, for example, let's call this the V vector, which is the inverse of the direction of the ray. Okay, they are all in the direction from intersection point P. And at this point, for example, we also have a light source. Okay, the light, let's have the light actually a little bit somewhere here. We have the light source. So there is also the vector we compute towards the light source. Let's call this vector L. Okay, we have the light vector. We should be careful about how we compute the computing of these vectors, for example, V and L, the initial vectors are easy, right? I mean, V is just the inverse of the ray's direction. We already have it in our ray. Normal can be computed differently for spheres and triangles. The normal vector for a point P. First of all, we find this point P after we intersect our ray with all of the objects. So this point P is also known. So if we know this P, we can, if it's a sphere, for example, P minus the sphere's center give us the normal vector, and we keep all these vectors in unit length. Because we will be computing the cosine of the angles, and therefore we will be conducting dot products. So it's good to normalize these vectors. So we have a light source, and we may have multiple light sources, but I'm just going to do the summary with a single light source where we have the single L vector. Okay, another thing is, for example, we compute the half vector, right? The half vector was computed between the normal vector and the L vector, if I'm not mistaken. Am I right? Correct me if I'm wrong. So, yeah, actually it was between the V vector and L vector. I'm wrong, right? The half vector, compute the half vector, the vector between V and L, let's call it H, and then I compare this half vector with the normal vector. If the half vector is exactly in the normal vector, it means that the light directly is reflected in the direction of V. So that's why instead of computing a reflection vector of this L vector with respect to N and comparing reflection with V for the specular component, we compute the half vector between V and L and compute it with respect to N. So N dot product H will be the amount of, it will be used to indicate the amount of specular reflection at this point, how shiny that spot is. And we're actually going to raise this to the power of S, this specular exponent, to compute that one. And the dot product between N and L will be used for the diffuse component. So this is for the specular component, this is for the diffuse component. And in all these things, the intensity of the light, when we compute the radiance at this point, so we have the light and its intensity, we're going to take into account the distance from the light's position to P, whatever this distance is. You're going to reduce the intensity by the square of this distance. And there are different models. For example, we can reduce it by linearly. We can reduce it quadratically, or we may. So there are different attenuation models, but usually it's just a polynomial of second degree like this, and it's the simplest polynomial with second degree is just this d square. It could have been something like this: a times d square plus b times d and plus some constant, for example. It could have been a polynomial like this instead of when we are dividing this. And OpenGL actually allows you to provide all these constants A, B, C in this polynomial kind of attenuation, light intensity degrees at this point P. Okay, we have half vector, and okay, so this was for basic illumination model. So we compute the dot product between N and L for the diffuse, N and H raised to power specular exponent for the specular component, and we have the ambient component, which is just an ambient. In ambient component, there is no light distance. It's the ambient light available everywhere. We multiply all these intensity values or components, specular, diffuse, and ambient components, we multiply all of them with the reflectance coefficients of the surface to find the color coming from basic illumination model. And while we are doing that, we are also this light ray here from point P, we also intersect this with all the objects in the scene. This is our shadow ray, okay? The shadow ray, you may have used as the shadow ray the non-normalized version of this ray. The entire ray from P to the light source could be used so that when T is between 0 and 1, you find an intersection between 0 and 1 along this ray. It means that the light rays cannot even reach this point P. So there is no need to compute these diffuse and specular components. So that's something we do for shadows. And the final thing in the ray tracing, what we do is we compute the reflection of this view ray with respect to the normal. We compute this ray R, and this ray R is treated as if it's a regular image ray. So if this was, for example, ray at level 1, this becomes your ray at level 2, and you do the entire thing recursively, this exact same thing. You intersect with all the objects in the scene, and you compute the color for this ray at level 2, and multiply this with the mirror reflectivity coefficient. Whatever color you have for this ray, as if it was a pixel, you multiply it with the mirror reflectance coefficient and add it to your color here. Everything is additive, and at the end, everything is clamped if it's greater than 255, or however the way you compute the color, but everything is going to be in the whatever you write to the ppm file. It's going to be between 0 and 255 for each of these channels. So if you saturate, if your color gets saturated in any of these computations, you just write the maximum amount of the color. Also, you never get negative colors in any of these computations. So that's the summary of ray tracing as I remember. So is there any part that I missed, or do you have any questions about this summary? Exactly. Reflectance, this mirror reflection is exactly like as if our camera eye point is at P. There's only very small difference, right? In the original ray, there's this distance of our our eye to the image window. When we are generating these rays, we take into account this d and to find the pixel coordinates, right? Here in this one, there is no such pixel. This point P acts as if it's the pixel actually. We may imagine there's some, I mean, it may be the camera is actually behind somewhere here, and this is the pixel that you have. It may be better to treat it that way. I mean, the missing thing is that this P, you may treat it as if it's the eye point, but then when you're doing the intersections, for example, if you're checking for intersection point greater than 1, this you shouldn't do it for this ray, because if there's an intersection in which t is less than 1, which means that there's no image window in front of this. So even you have a very close intersection with another object, and t is, for example, 0.5, you should still see a reflection of this object here. Okay, you should be careful about this. I think it may be also reasonable to treat this P as if the center of a pixel, and there is some imaginary camera location E, maybe at some place behind this. It doesn't change anything actually. You already, I mean, the rays direction is here. P is your race starting point. It's like, would it change drastically if I just move this E to the center of the pixel and form my ray from here at the center of pixel? I don't think so. I mean, it doesn't change that much. Only thing you have to be careful is when you do the intersections, whether should you see something that is between 0 and 1 or not. I mean, should you check for t greater than 0 or t greater than 1 if you want to see only the objects that are in front of this image window. It just changes that, but other than that, I think you treat them exactly the same way. And yeah, I think you can do the check with t greater than 0, because we discussed this in class before. It makes naturally our since the image window actually is behind the focal point, so the way we put it in front of the focal point is to have the image seem upright, not up bottoms up. So so it may be easier to do that. So there's a question from Selim. Let me read it. Instead of keeping track of our object when we check whether there's a shadow or not, we may use an epsilon value. But this, yeah, when you use it, yeah, exactly. So these, if there's a, you're right. I mean, if you use an epsilon value and there's a very close object, a very close triangle, if the objects are too close to each other, the one that is closer to you may actually be a reason for a shadow. So keeping track of the object is a better idea. But when you usually have this epsilon really small, larger, which is also larger than the floating point precision, usually if in your scene you have very close objects, such kind of surfaces should be corrected. Maybe you can just remove one of the surface and make it another object, or you may pre-process your scene to get rid of these very close surfaces to each other. So this happens in games too. For example, you have one surface, some rectangle, you put another rectangle in front of it, and if they happen to be very close to each other, in OpenGL, for example, we are going to see another artifact of another problem with this, which is called Z fighting. In order to determine which object is in front, which object is at the back, we will be doing something called depth test. And because of floating point precision, these very close surfaces, the renderer is going to think at certain points the one of them is in front, the other is at the back, and vice versa. So yeah, for high, I mean, yeah, for shadows, I mean, shadow really usually is going to make sense when the objects are far away from each other. I mean, not if you have a really close object, it may not be so critical to not produce shadow due to that, because it may be the case that if they're really so close to each other, you may not even see the object that is at the back. Okay, so if imagine there are objects very close to each other. Okay, are you going to see the shadow or the other object that is on top of the other object which is close? Probably the shadow is not going to be visible anyway. So visually you may not see the difference if there's a very close object. But there are different ways. So there are lots of practical problems like this in computer graphics, objects being too close. For example, even Kadir, for example, your assistant Kadir Cenk is making announcements about correction in those XML files. Some of them actually may go unnoticed. So these are really practical problems when the triangles are too small. There may be triangles that are degenerate with zero area, with triangles that appear just like as lines. So these are just practical problems you can either solve by having your renderer accept those cases and treat those exceptions accordingly, or you can pre-process your triangle and get rid of all these degeneracies beforehand. Actually, in Blender, there is a like quality check kind of module plugin which you can give your polygonal model, and it will tell you whether such degeneracies are there, whether things are too close to each other, multiple triangles at the same place, or all these things are like, there is some definition of a quality of a polygonal mesh. So these things may happen. But yeah, you can get rid of. Oh yeah, there's also close vertices may be merged together automatically. So yeah, in pre-processing you can make your polygon in such a way that it doesn't have these edge cases or degeneracies. But they're all very good points. The epsilon, depending, yeah, actually, yeah, that's another thing. Instead of choosing a fixed epsilon beforehand, you can look at your scene and see whether you can select epsilon after you see your scene and see how close the objects are. Yeah, you can do that. We can calculate what epsilon should be. But I mean, these are really, as I said, very visually, some of these may not even be visually producing any difference. So but having no epsilon, having epsilon is equal to 0, definitely is going to produce some visual problems. Those shadow spots, shadow dust, shadow noise will appear if you just use epsilon 0 and don't do this check self-intersection with the object. That will be a visually bad thing. But if you just use some epsilon, it will just get rid of it in one shot. These are just heuristics that you use to make your scene appear nicer. Okay? Any other questions? Okay, so I think this wraps up the ray tracing, our basic ray tracing algorithm nicely. And now we are going to talk about things that some additional topics that we also may apply to our ray tracer. The first thing is, for example, data structures. I mentioned about these earlier in the previous weeks, how to speed up. So the biggest speed up we are going to get in ray tracing, I told you that to have some kind of a hierarchical representation of our virtual world in which these ray object intersections are optimized instead of a linear intersection going over all the objects in our scene. We can have a logarithmic, very sublinear complexity ray object intersection. When we calculate how close we can see, should we take arbitrary value like t? Oh, the near distance of the camera. When you have your ray object, I mean, if you have, so let me get your let's see if I get your question correct. So if this is the image window, okay, a pixel, I'm looking at the image window from the side. Okay, now there's this eye point E. Now what we do is we form this ray, and this is the distance of our eye to the image window. So this is the image window, and I have a pixel here. Now when I form my, and this is the distance D, so if this is the pixel coordinate P, basically the length of P minus E is equal to D. Okay, now in order to determine how close we see the objects, how close we can see, usually this is called the near distance. So D actually here is the near distance of the camera. In OpenGL, for example, we don't see any objects that are closer than the near distance. So it really depends again whether you want to see objects that are as close as zero distance to your eye point, your focal point. But in systems like OpenGL, there are two distances that are defined: the near plane and the far plane. There's also a far plane, which actually is just used to, so we're actually, whatever cut out pyramid we have here, this strange shape is called, actually this part of the virtual world is called the frustum. It's a volume, it's a viewing volume, which is of the shape of a cutout pyramid. So this is like a pyramid where you have its top cut out at this near plane. So we see everything in this viewing volume. So in order to produce compatible images with what OpenGL does, you can also have the minimum t value to be equal to this. So if you have your ray as a non-normalized ray like this, E plus P minus E t, okay, if this is your ray equation, in this case, the value you would use to see objects that are far away than the near plane would be t is greater than 1, right? So greater than or equal to 1, either on the image plane or beyond this. So you may use this one. And in the assignment, it will not make a difference because we will not have any objects that are between the eye point and the image window. So there will not be objects here. But you can also have your near plane. I mean, even if the near plane is at distance d, when you have t, I want to see objects that are larger than t is greater than 0, that are between here. It wouldn't make. I mean, you will, if there's an object very close to you, and don't forget. I mean, I'm drawing these images in such a way that it shows that your camera is like occupying most of the scene. In reality, it's not like that. In reality, I mean, this distance d is something very small. I mean, actually, in real life, it's just the distance between your focal point of your lens and your retina is maybe ½ centimeters, 3 millimeters. I don't know, it's very small. So therefore, this D near plane actually is something very small compared to the far plane's location. So it wouldn't take much difference whether you use this one or this one. It will only you will see objects that are very close to you. You will be able to see them that are between E and P. Okay. So it depends. You can choose any value you want. In the assignment, I think, as I said, you use t is greater than 1. But this, if you use it like this and you write your ray tracer for the reflection part, reflection rays, you should treat that intersection point P as if it's your pixel coordinates, so that if there's an object that is actually closer to you, you want to see its reflection. You shouldn't use t is equal to, so you just treat the point P on the object when we compute the reflection rate, the point P on the object, treat it as if it's the center of the pixel that you see here. So you see anything that is in front of this pixel, you'll be able to see it. Okay? Yeah, when you're forming your ray like this, treat this point P. Maybe you can have some imaginary point E behind the focal point, maybe some imaginary point behind this point when you're forming your ray. So it really depends on how you implement it. Whether you may either have some imaginary point E behind to form your ray and still use the same t is greater than 1 here, or you may keep track of the level of the depth of your recursive ray tracing and use different t values at different depths. For example, if it's the first level, use t is greater than 1. If it's the second, third, or further levels in the recursive ray tracing, use t greater than 0 as your threshold. You may do it like that, or the other way around. Okay. So yeah, I think you should be able to generate all these very nice images that Kadir shared with you. They are really nice scenes. These objects, especially like the Otto car model, it looks really nice. I mean, all these reflections are underneath. I think I have them here, right? Oh, the scenes, actually, I remember I downloaded it someplace. I think it was in my laptop at home. Yeah, but yeah, you must have seen those output example sample outputs. They look really nice, and it will be really rewarding that your program is going to generate those images too in this assignment. Okay, now let's go ahead and start data structures for graphics. The data structures part is actually composed of two main parts. The first part is how do we represent the objects themselves, efficient data structures to store those triangles, faces of objects when they become really large. For example, if I have a triangular mesh, should I have a file in which each triangle is listed separately, line by line? So for each triangle, I will need 3 vertices. So one way to do that would be, for example, if you have a very large triangular mesh, since these are just triangles, why not list? It may be a triangle list. I may have a file format in which I list every triangle one by one. If I have 10,000 triangles, I will have 10,000 lines, which is like for every line, I will list 9 values. Chords for vertex 1, coordinates for vertex 2, coordinates for vertex 3. So 9 floating point values for each triangle, and I do it for all the triangles. So this is one way, for example, to represent this triangular mesh. But is it the most efficient one? No. For example, one thing you will notice is that if we have a triangular mesh, which actually forms a closed surface, okay, you see that certain vertices are shared among the triangles, okay? So if this vertex is shared, for example, between these 5 triangles, it means that if I use this version I will be repeating the floating point coordinates of this vertex redundantly for 5 times. Instead, if I first, for example, list the vertices separately and give them some integer IDs, for example, if I give an integer ID to this vertex saying that this is vertex number 1, and if this is with this single integer index, I can actually indicate each triangle by 3 integers instead of 9 floats. For each integer, I would say, for example, this triangle is vertex 1, vertex 5, and vertex 9. For example, if this is vertex 5, this is vertex 9, I can indicate each triangle as a list of vertices like this as integer indices. So it will actually save a lot of space. And we may also think about data structures when we're doing these. There are actually, in computational geometry, for example, there are data structures which are used especially for space surfaces like this. There is one thing called doubly connected edge list, DCEL. You're not going to see it here in this course, but it allows you, for example, to walk over the boundary of a triangle by each, for example, instead of having the vertices and triangles like this, maybe I may do something, I may store these edges. Why do you store these edges? For example, if I just have the vertex information and the edge the triangle information, for example, can you walk through, for example, given a triangle, can you find its neighbor triangles easily? This really depends on what kind of a data structure you'll be using. It really depends on what kind of queries you want to make on this object. For example, if given a triangle, if you want to get to the neighboring triangles quickly, you may have a data structure organized in such a way that it will give you this information. For example, I can have in the doubly connected edge list, for example, it's actually really a table of edges, vertices, and faces. So, and it's for example, it's a really generic model that it can have any face, not only triangles. We may have any polygonal faces. So, for example, we may, but each edge has a next pointer, for example. By using these next pointers of edges, you may walk around the face in actually in counterclockwise order. So the next of this one would be this. So each edge actually is composed of 2 twin edges. They're called half edges because this edge, every edge bounds its faces on its left. So this edge, for example, is shared by these 2 triangles, and its twin edge is this one, and its faces to its left as well. So, but anyway, this is not our topic. I just wanted to just show you that there are data structures which are really different from each other that may help you to solve certain optimization issues, efficiency issues when you're doing queries on these objects. So the first part of this data structure for computer graphics will be dealing about how we represent those virtual objects, the data structures we use for those objects. I'm going to be talking about these mesh kind of data structure. And the second part of these slides are going to talk about efficient organization of these objects in a scene with these hierarchical data structures that allows us to query, for example, intersections efficiently. So those are basically the 2 parts. Let me go ahead and start this PowerPoint presentation, and I will be using the annotation to annotate on this when I need. So let me see, the pencil tool, it is nice. Okay, so can I still, no, I need to stop annotation to be able to go through the slides. Okay, so yeah, I already summarized this part. So today, how we can explicitly represent those objects. We are going to talk about triangle meshes. And there are different formats for all these things. For example, what you want to store with the objects. For example, the color of the material data you want to store with the object itself. For example, you may also want to store the pre-computed normal vectors along with the object as well. Or you may store a texture image which gives different color to every point on the surface differently, different colors. So we may, these triangular meshes, they may come with textures, they may come with normals, or different things. Okay, so really there are different formats for these, and some of the triangular meshes, they even contain, for example, an information about their skeleton. When you're going to use them in animation, the joint information, for example, if this is a triangular mesh, maybe humanoid, an avatar, for example, and those triangular meshes are not just static objects like this. A skeleton model, actually it has a name in Blender. I forgot the name of that skeleton model. Does anybody? Yeah, armature. Yeah, thank you very much. Yeah, that armature, for example, is really important to show you how you're going to change the different parts of the object with respect to each other to actually provide animations. There are really nice tutorials on YouTube. If you're interested, for example, in 1 or 2 hours, you can actually model yourself, your own object, a humanoid avatar, and provide some, for example, walking, running animation, and these can be imported into game engines like Unity in a matter of minutes. So it's really very, I mean, after talking all these things and doing all these programming, I mean, after you write your ray tracer with just pure C++ code, seeing how all these things are done very easily with game engines actually a bit frustrating, okay, because it does everything automatically for you. You just, for example, interpolating between different animation models. You're walking your avatar by hitting with certain keyboard shortcuts. You start running, it immediately goes to the running motion, but with a smooth blending from walking to running animation. All these things are some advanced topics that we are not going to cover in this course, but computer animation is all about this dynamicity of the objects. So today we are going to see how a certain format, I think this format that we are going to see about triangular meshes is the poly format that I have shown you earlier. We have this cappuccino model. Well, I didn't save it as a cappuccino. So when we open this with MeshLab, where's my MeshLab? Here. So let me open recent files. Yeah. So this is an OBJ for, oh, I changed this location. So open, import mesh. Where is it? It's here. Oh, this PLY model. That's also, yeah, I think we're going to learn this poly model. But this OBJ format is, for example, I think it's binary. Let's see whether it's binary or not. It's here. So when you try to edit it with Notepad, no, it's not actually binary. OBJ is also ASCII, so you can actually read inside this OBJ file. So there's some, I think this is like the name of the object, some metadata, material library, or material. So it indicates some material. If we had some material, so the material of the cup is actually in a separate file, which we should have downloaded. Maybe it may have been downloaded here in this zip. Yeah, it's right here. That it was complaining, the MeshLab was complaining about not being able to find this MTL file. Let me also take it out of this zip and copy it here. And let's see how it looks like. So this is its material. Oh, look at these values. These are all very familiar, right? Reflectance coefficient. NS. What can NS be? 225, a large value. It's the specular exponent probably. A shiny cup. So it's ceramic, right? Ceramic should be shiny. Oh, so they even give it name to the ceramic, new material. It's a very high specular exponent. Uh, its ambient reflectance coefficient is different from its diffuse reflectance coefficient, and it's different from specular. Look at this, is exactly what I told you before. It has like 3 different colors. If it's like a white object when it's reflecting the ambient component. It's like a diffuse component is a bit dark, lighter gray, and specular is also gray, half gray. And this KE, I think this may be whether it may be some objects may emit color themselves, and like a light source. This may be the emitted color emission of the objects. It's 0, 0, 0. It's not emitting anything. Or it may be our reflectivity coefficient, or maybe it's this one, I'm not sure. So, but whatever it is, you see, yeah, diffuse is the actual color of the object. So that's the dominant color of the object, is the diffuse one. Because diffuse color is the color that we see due to the light sources. That's actually in these basic illumination model, the diffuse component is the dominant component. Because ambient color usually is a low color in this environment, and specular exponent, we only see it if the light ray is, we only see it in that specular patch, in that shiny patch. Other part of the objects do not have the specular component. So the dominant part is going to be the diffuse. But whether you call this, you may call it the actual color, yeah. Oh, there is also where there is this normal PNG, base color PNG, where oh yeah, there are these other material normal. So the normal vectors are is provided as a PNG file, as a texture file. So it's really, actually these are texture maps. We are going to talk about texture maps this week as well, in the second part of the, after we talk about data structures for computer graphics, we'll talk about texture mapping and how we can map some arbitrary colors or properties to points on the surface. I don't know whether how they're used in this material. So this is kind of a separate illumination. It has normal, base color, roughness, material. So I'm not familiar about these things, but it's really, as you can see, it's an ASCII file that you can read. And this is, look at this. Actually, I wanted to show you. Yeah, these are they may be conventional names, and here the vertices are listed first. How many vertices it has? Many vertices, 4, 5,000, 6,000, 8,000 and going, 10,000, 11,000. Whoa, no, it's still a vertex? No, this is, yeah, this is 11,000 after a certain point. The V's are, yeah. Wow, what is this? I think this is the texture coordinate for that vertex. We haven't seen texture mapping first, but these are the texture coordinates. So these are the vertex coordinates, the XYZ coordinates of the vertices. And we have about 15,000 vertices, and it comes two-dimensional coordinates for the vertices. Again, another 15,000 of those probably. These are texture coordinates, which are given between 0 and 1. They are actually map this vertex to a particular pixel on our image. We are going to see how we will be using these texture coordinates for texture mapping. But now I should go probably to 30,000 something, because they have exactly the same number of, so it has to be provided for every vertex. And then I have vertex normal vectors. So in this triangular mesh, the normal vectors are also pre-computed and given to me here nicely. Another 15,000 of those normal vectors. And when I come to 45,000 or something, now I have the face information. Wow. This face information looks interesting in this OBJ file. use material ceramic. So the faces, this is the part where we use the material. Oh, since these are quads, I think the first one is the vertex ID. So these four vertices form this quad. So it's all one. Oh, this is interesting. 2, 5, 6, 3. So I don't know what these numbers are. I think they are indices to vertices, but why do you provide like 3 things for a vertex of a quad? I'm not sure. So we should just, I don't know the OBJ file, but we can guess. This is a really good question. Can we have a normal vector for each? Does it make sense to have a normal vector for each vertex? So why don't we actually? All right, where's that? My GIMP, and then I'm going to have a break. So it's a really good question. So what happens is that this is actually approximate, exactly, they're the average of connected faces. So Jella actually answered this correctly. So what happens is that usually when we have these objects, for example, if you look at this is a smooth cup, right? I mean, although we have these faces as polygonal objects, instead of having normal vector, if we have normal vectors for each face, the reason, for example, we see in your ray tracer models, we have these objects, for example, the car model or some other models. Each triangle in those models, you see actually the boundaries of the triangles. The faces of the objects, they do not appear smooth. Actually, let me just give you some example here. Let me just download the homework files to show the example. So where are the homework files? Somewhere here. Yeah. The scenes, sample scenes. So let me download this. And if you look at the sample scenes, outputs, backface, culling, on, yeah. For example, let's look at the car. Oh, I can only see it. Let me. Okay, users, desktop, cohorts, car, BPM, car, PNG. Okay, now look at this one. I mean, it's not really good visually to, let me get my camera. So to see all these individual triangles, the boundaries between them, right? I mean, look at the top of the car. I mean, whoever modeled this car, I mean, wanted to probably make the surface of the top of the car look smooth. But if we have a normal for each face like this, the boundaries, since these neighboring faces, they are facing in different directions, their normals are a bit different, so the diffuse color we compute for the entire surface is based on this normal vector, which is constant throughout the surface. Therefore, each face has a different diffuse color, which makes the boundaries seem visible. Now, the way to actually cheat a bit about this is to use for each vertex, we can actually compute a normal for each vertex here, the shared vertex between faces. We can actually assign a normal vector to this vertex as the average of the normal vectors for its adjacent faces. Incident faces, not adjacent. So a vertex is incident on a face, okay? Adjacencies between objects of same type, okay? For example, a face may be adjacent to another face. Two faces are adjacent, but a vertex is incident on a face, okay? Now, when we if we assign different normal vectors to each of the 4 corners of this quad, they will have different normals, right? What will happen for a point inside the triangle? I also compute its normal as an average of these 4 vertices incident on this face. What it will do is it will actually, all these boundaries of the faces, they're going to disappear, and we are going to, the coloring, the shading of this surface is going to appear as if it's a smooth surface. Okay, it will just appear, so this is like cheating, as I said, it will appear as smooth, but if you still look at its silhouette from the side, or if you look at its shadow at some surface, you're going to see the boundaries, you're going to see linear, these surfaces are connected to each other linearly, but this technique of averaging the vertex normals incident, averaging the face normals incident on a vertex and assigning it to vertices, and then for a point inside a face, because we're not dealing with vertices only, right? Our ray intersects with a point inside a face. So what is the normal of this point inside a face? We just say that let's average, actually interpolate. This is not the direct average of those 4 things. Depending on how close it is to which vertex, we may interpolate the normals according to their distances to the corners, and the normal of this. So in other words, it will be something like this. On a surface, we may have normals facing in different directions, even on a triangle. Okay, so that's why we have vertices at normals, normal vectors at vertices. Okay, so this was... Okay, so now let's have a 10-minute break, and after the break we are going to go detail. But the first part of this is already done. I mean, we are going to talk about all these, this format similar to this one, in which we have vertices and faces stored separately. Let me stop recording now and see you all in 10 minutes.